All right, section 2.5, part 4, the final part of section 2.5 is about continuity and how continuity relates to limits. So we're going to be talking about a function being continuous at a point, what makes a function continuous at a point, and then also continuity of a function on an interval. So our big question for this entire section is, what does it mean for a function to be continuous, and how does it relate to limits? Because it's going to relate to limits, of course. Okay, so we say that f of x is continuous at a, means that inputs near a are sent to outputs near f of a. So I'm going to draw, how about y equals x cubed? We know that all polynomials are continuous, smooth continuous functions, right? So let's think about y equals to x cubed, that graph. And how about specifically the point 1, 1? Or actually, let's say that's the point 2 here. Let's do the point 2, 8. Okay. So what makes x cubed continuous at that point? Well, if we were to choose values close to x equals to 2, so like 1.99, 1.999, right? Choose values closer and closer to 2 on the left side, and then like 2.00001, 2.001, right? Values that are just to the right of 2. The y values that correspond to those x values would be values that would be very close to 8, right? So 1.99 should map to a value that's very close to 8, and the 1.999 should be a value that's even closer to 8, and then same thing with those values to the right. So this should be sounding familiar, right? It should sound like limits. So a function will be continuous at an x value, so at a point, if when you take the limit as x approaches that value, so in this case, as x approaches a for our definition, that the limit is equal to the function evaluated at a. So we have these, remember these 3 cases of when a limit exists, okay? So the first case that we talked about was when the limit of the function as x approaches a ended up being equal to the function evaluated at a. So when the function was continuous, right? That point would be a comma f of a, which is also a comma l in this case. So when l ends up being equal to f of a. Okay. The other case, or the second case, was the limit existed, but the function evaluated at a was not equal to L. It was equal to some other value, right? So this up here would be f of a, right? This would be the point a comma f of a. And then the last case was when the function was undefined at x equals to a. So f of a is undefined when there's like a hole in the graph, okay? So remember, for these 3 cases, so when we were talking just limits, okay, remember each of these cases the limit exists, but in no case did the value of f of a have any effect on the limit. However, the value of f of a is an integral part of the definition of continuity at x equals to a. So now we're talking continuity of a function at a point, and we are going to care what the value of the function evaluated at a is. Okay, so here's our more formal definition of continuity. Remember, before we were using just kind of the intuitive definition of continuity, where if you could trace your pencil along a graph and you didn't have to lift up your pencil, then the function is considered to be continuous. And this is actually a definition of continuity at a point as well. It's not on an interval yet. We are going to talk about continuity on an interval. This is the definition of continuity at a point. So f of x is continuous at x equals to a if the following conditions are true. So if the function evaluated at a exists, if the limit as x approaches a of f of x exists, and then if the limit as x approaches a of f of x is equal to the function evaluated at a. So basically, if 1 and 2 agree. So we're going to be treating this as kind of a checklist for helping us to determine if a function is continuous at a point. If a function fails to satisfy any one of these three conditions of the definition, then it's not continuous at x equals to a, and is said to be is discontinuous at x equals to a. I'm going to get rid of this. Okay, so there are three different types of discontinuities that we talk about. So the first one is removable discontinuity. This is going to be whenever you have like a hole in the graph, or like it can be, so basically if we go back to our three cases of where the limit exists, so case 2 and 3 where the limit existed, but the limit didn't match the function evaluated at a, or the function evaluated at a was undefined, right, giving us a hole. That's when we end up with a removable discontinuity. Then non-removable jump discontinuities. So you guys have already run into these. It's just now we're actually going to be talking about them as points of discontinuity and then kind of labeling the type of discontinuity. So this happens with like piecewise functions. Okay, and then non-removable infinite discontinuities can happen like basically anytime there's a vertical asymptote. So rational function or some sort of piecewise function as well can happen. Okay, so we're going to first look at what removable discontinuities look like and how to identify those. So if the limit exists but is not equal to the function evaluated at a, then we say f has a removable discontinuity at x equals to a. So when we have a removable discontinuity, we can think about making f continuous at x equals to a by redefining the function evaluated at a. And we would want to redefine f of a as whatever the limit as x approaches a for f of x is. Okay, so we have a rational function here. And this is a rational function that's already in factored form, and we can see that we have a common factor in the numerator and denominator that will cancel so that we have x plus 3. Now you guys know from your pre-calc knowledge that when you have a common factor that cancels, we know that there will be a hole in the graph at x equals to 2. Okay, so we know that there's going to be a point of discontinuity. But now we're going to look at this from a limits, a calculus perspective. So let's pretend that we don't know that there's a hole at x equals to 2. Okay, we want to know, is f continuous at x equals to positive 2? Okay. Well, if we're going through the checklist, f of 2 would give us 0 over 0. So right away, we know that there's a point of discontinuity at x equals to 2. In this step, we know f will be discontinuous at x equals to 2. But we have to keep going to help us identify what type of discontinuity occurs. So if we take the limit as x approaches 2 for f of x, I'm going to put that original function in here. Okay, so direct substitution initially would result in 0 over 0. So then we can take the limit as x approaches 2 of the simplified version of the function, which ends up giving us 5. So the function is discontinuous at x equals to 2 because we end up with 0 over 0 when we substitute 2 into the function. However, the limit exists. When the limit exists, but it's not equal to whatever the function evaluated at that x value is, we know that there is a removable discontinuity. Okay. I know Mr. Amnath prefers the term removable discontinuity over whole, but we know from our pre-calc knowledge that there is a whole at the point 2, comma, and guess what? We'd want to fill in that y value with 5. So the graph of f is going to look like the line x plus 3. So slope of 1, y-intercept of 3. And there will be a hole at 2, comma 5. Right? We would want to fill that point in as 2, comma 5. Okay, so here's a piecewise. So for piecewise functions, you can check each piece to see if there would be some sort of domain restriction or point of discontinuity in any of the pieces of the function. But also you want to check at the endpoints of the subintervals of the domains for each piece. So like we want to know, is f continuous at x equals to 2, right? Because we can see here that the function, something happens at x equals to 2 versus whenever x is not equal to 2. So first of all, f of 2 is 2, okay? So we're off to a good start. F could be continuous at 2. And then we take the limit as x approaches 2. This is a piecewise, so why don't we take the one-sided limit? So the limit as x approaches 2 from the left, okay? We can actually end up substituting into this first piece here, right? Because the graph everywhere except for x equals 2 will look like x squared minus 4. So we get negative 2. And then the limit as x approaches 2 from the right, we would also substitute in there and get negative 2. So the two-sided limit is negative 2. So the limit exists as x approaches 2. However, the function evaluated at 2 is a different value. So because step 1 and step 2, or condition 1 and condition 2, from our definition do not agree, we know that there will be a removable discontinuity at x equals to 2. So let's think about this graph. So everywhere except for x equals to 2, the graph will look like x squared minus 4. So that's x squared shifted down to, shifted down 4. I know that should be closed. Okay, but whenever x is equal to 2, y is equal to 2. Okay, so this would be like case 2 of whenever the limit exists. It's just the function evaluated at that value of x is different. Okay, so the next type of discontinuity we'll look at is non-removable jump discontinuities. So there's two different types of non-removable discontinuities. There's jump, and then there's infinite. So a jump discontinuity occurs if the one-sided limits exist but are not equal. So like if we have the limit as x approaches a from the left equals, let's say, m, and then the limit as x approaches a from the right equals some other number n. Okay, so the one-sided limits don't agree. They both exist, but they don't agree, and that should be a plus. Okay, so remember, each piece of this piecewise is a polynomial, so each piece is continuous over its implicit domain. So we're going to check, we want to know, is f continuous at x equals to 2? Okay, so f of 2, 2 looks like it falls in that second interval, so f of 2 is 4. So we want to then take the limit as x approaches 2 piecewise, so we'll take the one-sided limits. Okay, so I'll substitute into the first piece. And then the limit as x approaches 2 from the right. Okay, so the two-sided limit does not exist because the one-sided limits don't agree. And when the one-sided limits do not agree, we know there is a jump, a non-removable jump discontinuity at x equals to 2. It's non-removable, have it? Yeah. Okay, so let's graph this guy. So when x is strictly less than 2, the graph will look like negative x. And then for x greater than or equal to 2, the graph will look like x squared. So you can see that there is a jump in the graph at 2. All right, non-removable infinite discontinuity is the other type of non-removable discontinuity. So we say f has an infinite discontinuity at x equals to a if one or both of the one-sided limits is infinite. So basically, if the limit as x approaches a from the left is equal to positive or negative infinity, or if the limit as x approaches a from the right is equal to positive or negative infinity. Now, it just has to be one of the one-sided limits equal to positive or negative infinity. Like you could have the limit as x approaches a from the left equal to a number, and then if the limit as x approaches a from the right is equal to, say, positive infinity, there's an infinite discontinuity, okay? Okay, so just from our prior knowledge, we know that at negative 2, x equals to negative 2 would make this function undefined. So there's a potential for a point of discontinuity. So we're going to show, but let me ask, is f continuous at x equals negative 2? Well, f of negative 2 is undefined. So we know that it's not. But now to specify the type of discontinuity, if we take the limit as x approaches -2, okay, we would end up with 1/0 when we do direct substitution. So then we have to think about the graph. So we know the limit doesn't exist, but we need to be able to state why. So the limit as x approaches -2 from the left, and the limit as x approaches -2 from the right. Okay, so this graph is 1/x shifted left 2. So that means that the vertical asymptote gets shifted to the left 2. Branches get shifted to the left 2. Okay, so limit as x approaches -2 from the left looks like we get negative infinity, and from the right we get positive infinity. So this limit is just D and E, the two-sided limit. And both of the one-sided limits don't exist, right? Because they're equal to, we're saying they're equal to positive or negative infinity. But just if we had looked, the second we got this first one-sided limit, we knew immediately there's an infinite discontinuity at x equals to -2. Okay, so is f continuous at x equals to 0? F of 0 is, it looks like 0, right? It would be the square root of 0, which is 0. The limit as x approaches 0, take the one-sided. Okay, so from the left, actually let's do from the right first. So the limit as x approaches 0 from the right would be 0. But the limit as x approaches 0 from the left, we would get 1/0 with direct substitution, which tells us there's some sort of asymptote, vertical asymptote there. So thinking about this graph, when x is less than 0, and then when x is greater than or equal to 0. Okay. So the limit as x approaches 0 from the left would be negative infinity. So right here, we know there is a non-removable infinite discontinuity at x equals to 0. Okay, we are not going to graph this complicated piecewise function. Okay, so let's explore each piece first. So this first piece, 1/x plus 3, has an implicit domain of all real numbers except for x equals to -3. Well, -3 lies in this domain. So if we were to go through our conditions from the definition of continuity at a point. So we want to know about x equals to -3. Well, first of all, f of -3 is undefined. But the limit as x approaches -3, it doesn't exist. You guys know what that graph looks like. And if we take the one-sided limits, right? The one-sided limit as x approaches negative 3 from the left would be a negative infinity, and then from the right would be positive infinity. Okay, so this is D and E. But we therefore know that there is a non-removable infinite discontinuity at x equals negative 3. I'm going to give myself another page here. Okay, so we then need to check for potential points of discontinuity at the endpoints of the subintervals. Okay, given for the domains. So next we would want to check negative 2. So f of negative 2, it looks like, would be 1. We'd substitute in here and we get 1. Okay, then the limit as x approaches negative 2, we have to take the one-sided limits here. For the, as x approaches negative 2 from the left, I would plug in to the first piece. So we get 1. And the limit as x approaches negative 2 from the right, we would plug into the second piece and get 1. So the function evaluated at negative 2 is 1. The limit as x approaches negative 2 is 1. Those match, right? So the limit as x approaches negative 2 ended up being equal to f of negative 2. So therefore, we can say that f is continuous at x equals to negative 2. So now why don't we look at positive 2? Okay, so f of 2, ooh, typo here. Let's make this there we go. Okay, so f of 2 is 9. Get room substituting in here. Limit as x approaches 2. Take the one-sided. From the left, we would get 9. And from the right, we would get 4. Okay, so the two-sided limit is D and E. Our one-sided limits exist but do not agree. So therefore, there is a non-removable jump discontinuity at x equals to 2. Okay, and then last, let's have a look at 4. All right, so first f of 4. Ooh, f of 4 is undefined. Okay, so right away we know there's a point of discontinuity at 4. But let's see what type by taking the limit. Okay, the left-sided limit would be 16. The right-sided limit would be also 16. Okay, so the two-sided limit, ends up being 16. However, the function's undefined. So we can actually say that there is a removable discontinuity at x equals to 4. So check each, so for piecewise like this, and if you're trying to find points of discontinuity, check each piece, and then also the endpoints of the subintervals. Okay, so that was part A. Part B is asking us to determine the function's end behavior. Remember, I told you guys, when you hear end behavior, you should now be thinking limits at infinity. So the limit as x approaches negative infinity for this function, okay, so which interval has goes to negative infinity? Well, that would be this first, so x less than negative 2, right? That's negative infinity to negative 2. So as 1 over x plus 3 approaches negative infinity, as x approaches negative infinity, what does 1 over x plus 3 approach? Well, it's going to approach 0. Okay. And then the limit as x approaches positive infinity. Okay, we go to the last piece. Okay, well, what is 8 times root x approaching as x approaches infinity? It's also going to approach infinity. Okay, so those limits help us describe the end behavior. One side will end up approaching 0. Right? We'll end up approaching 0 from below. And then as x approaches positive infinity, the graph will also end up approaching positive infinity. And then some other stuff happens in here. Okay, so you guys have probably already figured this out. But basically, whenever you've been able to just use direct substitution right away to evaluate a limit, it means that the function is continuous at that x value, at a, whatever a is. So now we're going to transition to talking about continuity on an interval. So a function f of x is continuous on an interval, I, if and only if the function f of x is continuous at every point in that interval. So basically, if every point satisfies those 3 conditions that were in the definition of continuity at a point. Okay, so continuity on an open interval. So function f of x is continuous on an open interval from a to b if and only if the function f of x is continuous at every point on the open interval from a to b. So remember, open interval means that a and b are not included. So an example could be something like that. Okay. Every point between a and b is continuous, just a and b are not part of the open interval. Don't forget that all real numbers, so negative infinity to positive infinity, is also an open interval. So like we say that polynomials are smooth continuous functions, right? And they have an implicit domain of all real numbers. Okay, so a function can be continuous over its domain of all real numbers. Okay, a function can be continuous on a closed interval as well. So a function f of x is continuous on a closed interval from a to b, so where a and b are included. If it's continuous on the open interval from a to b, and if the endpoints exhibit the following behavior. So if the limit as x approaches a from the right of f of x is equal to the function evaluated at a, and the limit as x approaches b from the left, this should be from the left, of f of x is equal to the function evaluated at b as well. So an example picture of that. Okay, so right, this would be f of a. This would be f of b. So the limit as x approaches a from the right side is equal to f of a, and then the limit as x approaches b from the left is equal to f of b. So we're going to read this graph from left to right and determine the intervals where the function is continuous. So let's read left to right. So we can see that from negative infinity, it looks like, to negative 2, f is continuous. And then negative 2 to 2. Notice I'm not including 2 because there's an open circle here. It looks like 2 is defined. But if we were to take the limit as x approaches 2 from the left, we would get 5. However, f of 2 looks like it's equal to 4. Okay, and then from 2 to 5. And 5 to 6. And it looks like 6 is included. Okay, because if we were to take the limit as x approaches 6 from the left, we would get the function evaluated at 6, which is 2. Okay, and then from 6 to 8. 8 to 10, 10 to 11, and 11 to infinity. Okay, so these are intervals of x values in which the function is continuous.